much for the invitation. It's quite an honor. Tony Fredekis, founder and CEO of Okeanos Technologies. So Okeanos is developing an elegant microelectrochemical platform for the ultra-efficient desalination of water. Efficiency is king when it comes to desalination. It matters a lot, and it's not just about the cost of water, it's about our survival as a species. And here's why. We're currently getting our water from fresh sources on the surface, lakes, rivers, and streams, which are quasi-renewable, meaning we can deplete them faster than nature can replenish them, and underground lakes of fresh water, which were deposited by glaciers hundreds of thousands of years ago and non-renewable. Overdrawing from these resources as populations expand creates all sorts of problems. Environmental problems, including localized drought conditions, environmental pollution that results from the need to collect this water in a centralized format and distribute out to end users. Water is heavy to transport, burn a lot of fossil fuels doing that. Water scarcity impacts food prices. It also influences municipal budgets. Water rights are largely spoken for already by agricultural concerns, and as populations expand, municipalities have to bid for those water rights, raising taxes in the process. There is also political turmoil. Anyone from California knows as the Colorado River peters out before it gets to the Gulf of Baja or the Gulf of California, that water is consumed by a wide swath of Americana and Mexicana, squabbling over rights to the water. It's just promising to get worse as drought conditions continue. And you think our problems are bad. In the third world, problems are even more dire. About 80 countries around the world harbor half of our globe's population, and these people experience chronic water shortages. About 80% of all morbidity or sickness, and 40% of all deaths is directly or indirectly attributable to lack of access to safe drinking waters. So what's the solution to this problem? Well, we know that there are vastly expansive saline aquifers under most continental regions. These are relatively shallow saltwater lakes. We also know that the oceans are virtually limitless. We've known how to desalinate since the ancient Egyptian times, but only a handful of desalination technologies have ever been described. The most recent technological advance in the 1950s produced reverse osmosis, which represents the gold standard today. The problem with RO, reverse osmosis, and every other existing desalination technology is that it's energy intensive. It's too energy greedy. The levelized cost of water produced using these technologies exceeds the cost of water from these fresh sources on the surface. So what do people do? They mine fresh water on the surface, creating these problems, exacerbating the problems. In fact, many people feel that we're heading into a death spiral of Malthusian proportions unless we get the efficiency part of desalination fixed so that that perverse economic incentive is no longer functional. The U.S. Department of the Interior called for renewed interest in desalination efficiency research 10 years ago, yet most of the new technologies coming on the market represent incremental and relatively insignificant improvements to existing fundamentally defective, thermodynamically defective technologies. What's our solution? Well, our solution is to approach desalination from a completely different angle. We approach desalination instead of on a macro scale, like all of the existing technologies, where water is treated liters at a time, on a micro scale. And we micro-desalinate, literally 1/1,000,000th of a liter at a time. And then we go through the engineering headache of scaling that up to reach commercially relevant water flows. Why do we go through that headache? Well, it's because the energetics in microspace are far more favorable. The rules of physics and chemistry are different in microspace than they are in macrospace. The process that we've developed with the University of Texas under EPA support through the SBIR program is called electrochemically mediated desalination, EMD. And it's very simple to understand. Basically, what happens is you have water coming in through a microstructure. You can consider it the root of a Y-shaped microchannel, less than the thickness of a human hair. It experiences an anode at the bifurcation point of that Y. And what that anode does is that it strips electrons from chloride ions present in the water, and in so doing creates a charge imbalance. This process is called oxidation. It occurs at the speed of light. It's ultra efficient because it's limited by something called ion or electron transfer kinetics, not ion transfer kinetics. And in our case, when that happens, it produces an electric field gradient that, when positioned in front of a freshwater stream, prevents ions or any other charged species from entering it. In this design that you're seeing here on the lower left, you see a brine channel extending upwards from the little red region, okay, and that's the brine stream. The salts, the bacteria and viruses which carry external charges are deflected up into the brine stream, only fresh water passes through. So when we published this work about a year and a half ago, it generated quite a buzz because it established a new world record for specific desalination energy consumption. This process was carried out at the equivalent of 1.5 watt-hours of energy consumed per liter of water produced. The previous world record, established by the Affordable Desalination Collaboration with tricked-out reverse osmosis systems at scale, 100,000 gallons per day, or per hour, I'm sorry. No, that's per day, was achieved about a 2.0 watt-hour per liter efficiency. And in the field, reverse osmosis typically operates at from 3 to 4, even greater watt-hours per liter. So why is the process so efficient? Well, as I mentioned, it's not just because of the fact that we're creating our energy zone by stripping electrons rather than pushing ions through vast spaces and boxes, but also we only need to perturb a very small amount of chloride ion to generate the force necessary. On this slide, I'm showing you some scientific data in the middle, the shape of the electric field gradient that was measured from wet lab experiments. And anyone that wants to talk about this more, I'm happy to entertain technical questions at the booth. So if you want to see the process at work, you can see water flowing in. It's dyed with an anionic tracer. As we apply the voltage, you see that the tracer is directed into the brine stream, and we relax the voltage, and you see the equilibration. So that's desalination in action. And what we've done to scale this from the past year and a half is we've essentially chopped off the microchannels, focused on the micro desalination center. We've three-dimensionalized it, reconfigured it, improved it, packed it densely into a substrate, a sort of a micro fabricated matrix, and we've achieved the designs that you're looking at here. The one on the far right is a version 3. The one in the middle that looks sort of gold is our current version 5. This device has the equivalent of 20,000 of those Ys per square centimeter of active surface area. It's a 1 centimeter active surface area device, and I'm going to share with you here today information that no one outside of our company has heard yet and won't hear until our paper is published early in 2015. But we have achieved with this device an energy efficiency, a specific desalination energy consumption of 1.33 watt-hours per liter. So we've bested our previous world record. And we're also operating at scale here, so that is even more impressive. We're operating at about 1 mil per minute. The next step, and by the way, I showed there's some desalination results there in the lower left-hand scale. The desalination is on demand. When we apply the power, about 30 seconds later, after the electrochemistry gets equilibrated, you see the desalination taking place, and it continues until you cut the power. I have lots of data, again, I can show you at the booth for those who are interested. But where we are on the scale, if you look at the numbers on the far left, we're at about 4 orders of magnitude improvement in flow throughput from the academic device that we developed with the University of Texas. That one's on the bottom. You can see the flow rate column, 0.04 microliters per minute, all the way up to 500 microliters per minute, or half a mil. It's actually closer to a mil per minute. What we're going to do now, and the reason why I apply for grants, continue to apply for grants and attend award conferences, although not quite at the advanced stage that we're at now, is to get to the next stage, which is to linearly expand the size of our active surface area to about a 300 to 400 square centimeter surface area, capable of about 1 to 4 liters per minute throughput. Now we're talking RO levels of throughput. That system can be paralleled, and our partners, in fact, will be doing that for us through an Intel-style model into various types of integrated systems to serve various water submarkets. We're going to focus strictly, just as Intel does, on manufacturing chips and letting everyone else build their own specific type of computer or device out of those chips. We're going to focus on what we call these submodular cartridges or blades. They'll be about this big. I have a prototype of one of the miniature-sized ones I'm happy to show you at my booth. But we'll focus on those blades, partner them with verticals in the water space, and provide, through our business model, an incentive for as rapid a penetration of the water market as we believe is possible, given the conservative nature of the water market. So why are they going to adopt this product? Is it just about saving money? Well, partly yes. A lot of build-own operators like Veolia, GE Water, they take the risk of designing, building, and operating water treatment plants for municipalities, and they guarantee water prices, typically about 70 cents per cubic meter. Their overheads, the difference between that rate and their overheads represent their margins. Typically, they're pretty thin. When we come to them with a system that can either as a pre-treatment system reduce their overheads by about 50%, or reduce their total desalinated water costs by even more than 50% if you replace RO with our technology, there's a tremendous incentive there driving adoption. Where you can find our savings is not just in electrical power consumption, but also in the fact that there's a natural biocidal property to desalinating in this way. Hypochlorous is produced in millimolar levels. That reduces dramatically pre-treatment expenses. It reduces the footprint, reduces chemical expenses. We're a non-filter technology, no membranes to replace, no membranes to foul, no membranes to prevent fouling of through elaborate pre-treatment regimes. So yeah, in the future, municipalities and vendors that sell to them will operate far more efficiently. But what you should remember is even more important than that. And that is that today's centralized water distribution model, we believe, is a thing of the past already. With technology like ours coming online, what you're going to see is a more distributive water production model where people can generate water when they need it, as they need it, and where they need it. In this case, I'm showing you a picture here of a centralized model, a water treatment plant that's necessarily located next to these precious fresh sources around the country. They tend to be huge. When they're desalination plants, they tend to suck, tens of thousands of gallons in from the sea. You have entrainment issues with animals, et cetera. You have to transport the water, very heavy to transport, as I mentioned, out to the end users. All of this is grid-tied or dependent on the burning of fossil fuels in some way, shape, or form. You can transform that into a distributive model where you see our Iowa farmer here standing at his brackish wellhead, a system. An EMD system in the future can be placed on top of that wellhead to produce his water for irrigating his crops from a renewable brackish resource, obviating the burning of fossil fuels, the need to ship water, helping to alleviate a lot of those problems that I went through in my second slide, opening up the vastly expansive renewable resources in the process. Thank you.
Thank you. Questions? Got one coming to the microphone over here on the left.
These structures are microcapillary kind of structures. So do you have to pre-treat the water in some way to make sure that you don't clog up those channels?
That's a good question. So our limiting dimension is 50 microns. We typically, in our lab, we're running untreated seawaters. It's only allowed to settle in a sedimentation tank, and we take the water off the top. With a reverse osmosis system, in contrast, it's a filter-based system. And you have these limiting dimensions of about 5 nanometers, much, much smaller. And that's how you separate the micro salt crystals from the water physically. So there's far more of an intensive need for pre-treatment with a system like that. To answer your question, we'll probably incorporate a 60 micron filter, maybe a 30 micron filter at the most as a pre-treatment step in the field when we get to that point.
Can you talk about the life cycle, the cost model, and the deployment length? How long will these things last in the field? What's your projections?
Well, so right now we can speak from data that we've generated in our lab running our cartridges for months at a time. And we've built them in such a manner that we obviate nanoelectrodes that were present in the original academic configuration. We no longer use nanoelectrodes. We use something far more robust. We've yet to see any degradation of the anode surface material or the cathode surface materials. We expect by extrapolation that our systems will be quite long-lived, as are analogous systems in the chlor-alkali industry. The process, our electrochemical process, actually used in a completely different configuration for example, producing the chlorine that's used for natural seawater, chlorinated seawater pools. So this is a process of chloride oxidation to hypochlorous. And the electrochemistry, the metallurgy of that process at an industrial scale is very well known. Well, we've applied those lessons in our current massively paralleled EMD prototypes. So let's see, what was the first? I can't remember yeah, okay.
Tony, as you know, I live outside of Austin, and we've got reverse osmosis on our water and our well to take out sulfites and lime. Is this only for desalination, or does it have other uses, other things that it can clear out of the water? For instance, pathogens.
Yeah, so pathogens are handled with this process through a natural biocidal property of generating hypochlorous. Now we're generating millimolar levels of hypochlorous. It's high enough to be a biocide, but easy to clean through passive catalysis as a post-treatment step. So we run the product water through, it's analogous to a charcoal filter of sorts. It's actually much more stable than charcoal. It's a passive system, energy-free, that actually converts that hypochlorous back to chloride, but at such low levels it doesn't appreciably impact the salinity of the product water. So microorganisms that make it through our micro desalination center have to deal with the hypochlorous. This is basically very dilute bleach.
Yeah.
Now, there's also the fact that a lot of these microorganisms carry external charges, and just like the salts, they're deflected into the brine stream. So it's really only the ones that make it through that are handled with the hypochlorous. But to answer your question, our system is not suitable for addressing organics. We actually have a partner that will help us do that in an extremely energy efficient method. It'll break those organics down into charged species, which our system will then clear.
Got it. Cool. Any other questions? Tony, thank you. Great stuff.